So I'm a staff scientist at SOFIA, and I work mostly with two instruments, HAWC and Forecast. But today I'll be talking mostly about HAWC calibration and the data artifact. And before I start, I would like to apologize if you hear some loud noises in the background. That's my son. He is home from daycare since it is snow day here in Colorado, and he likes to play with his dinosaurs. So the loud noises are dinosaurs, but they are basically data artifacts in the audio of WebEx. So just keep that in mind. With that, here is my outline of the talk. I'll be spending a fair chunk of time on Hawk calibration process. From there, we'll go and see how to, if you have Hawk data already, how to look for the Hawk calibrations, what keywords to look for to make sure whether the calibration is done, what calibration was done, so on and so forth. And I'll also mention some of the data artifact which usually appears in this data, in these kind of data. I also have a list of resources and technical supports, which is listed here. And this is also listed on the meeting or the SOFIA School website. So please take a look. Uh, Almost everything that we will be presenting here today is in one of these three links that you see on the top. So I urge you to go and look at all those either Harper's paper or the Hawk data handbook and so on and so forth. And if you don't find anything, and if you still have questions, please feel free to send us an email at Sophia Help, and we'll try to help you out as soon as possible. Okay, with that, let's start with Hawk. For those of you who may have not heard of Hawk, Hawk is a imager and a polarimeter in the far infrared. And here is I just wanted to start with, I can't go into all the nitty gritty details of Hawk instruments since I'm talking only about the calibration today, and I have just a few minutes to do that. But anyway, here is a ray diagram of how the Hawk instrument looks. This end, if you see my cursor is where the telescope is. That's where the light comes in. It gets reflected through two of the field mirrors. It enters a system where we have our filter wheels and half wave plates. Once the light or radiation passes through it, it gets split by a polarizing beam splitter, and then it impacts your detectors, two detectors. One is reflected radiation and one is transmitted radiation. Both these detectors, we call it the R and the T array, the reflected array and the transmitted array. And the detectors in Hawk are a little bit different than what usually you may know, like you may have heard, you may have worked with CCDs and stuff. But for Hawk, it's basically transistor edge sensor bolometers. So each of the pixels that we are talking about when we talk about Hawk data has to do with it's an individual bolometer. And we have, as shown in the cartoon here, we have the R array and the T array. The R array is made up of 64 by 40 bolometers or 64 by 40 pixels divided into two sub arrays, R0, R1. And the T array is just one subarray made of 32 by 40 pixels. Uh, as I mentioned earlier, Hawk can do two types of observation, the total intensity or flux observations and a polarization observation. The total intensity is done by all these arrays. It uses all of the arrays, whereas the polarization observation is done just by R0 and 30. So here is again a description of what Hawk can do. These are Hawk's observing mode, uh, two observing mode, total intensity mode, that's basically imaging data, and polarimetry, where you can measure Stokes parameters of your sources you're observing. Both of these modes can be run in different configurations. One of them is called the NORMAC CHOP, which is a standard IR or far infrared observing technique where you nod the telescope along the CHOP direction and combine the data to uh, get your intensity measurements. Or you can do on the fly map where you move the telescope continuously across an astrophysical source and gather data from there to, again, to measure your total intensities. Both this configuration are also available in polarimetry, but I should warn you that for the polarimetry, the on the fly map is still in shared risk mode. We are still commissioning that mode. So it'll, for now, even though we offer it as a shared risk mode. With that, let's start with the SOFIA data product. This is true for any SOFIA data. So instead of listing all the pipeline stuff that the SOFIA data goes through, I thought I would list more about what do you get if you go to URSA archive and look for SOFIA data. What do you get and what do they mean? So SOFIA data is divided into different processing steps. And here I have listed 5 of them. Level 0 data pertains only to HAWC data. None of our other instruments have level 0 data. So level 0 data is just a raw instrument data that comes out from HAWC, which in case of HAWC, it's a standardized time series data. So it measures all the time series as the data comes in. On the other hand, level 1 data is a standardized FITS data. It's in FITS format. And that's what most of our other instruments like Forecast, PPLS, and XEs provide you. In case of HAWC data, the data is already modulated and chopped, not subtracted. Then we have level 2 data, where we take the level 1 data and correct for all the instrumental artifacts like dark subtraction, flat fielding, bad pixel remover, making sure the grids are proper, and so on and so forth. Then we go ahead and take the level 2 data, and when we do telluric correction and flux calibration. And last, the highest level data for HAWC is what we call level 4, which is if you take multiple level 3 data and combine them together, then we consider that as HAWC level 4 data. For example, if your data was taken on 2 different flights or 2 different series, and you combine them together to make a larger mosaic, like the one that Matt Hankins was talking about earlier, where he had a large survey of the entire galactic plane in forecast, and all those data was combined, that is level 2 data. In case of HAWC polarization, the maps we will produce that are Stokes Q, I, U are all level 4 data. But today we'll be talking mostly about how we get from level 2 to level 3. We have level 2 data, what happens during flux calibration and telluric correction. That's what I'll be talking about today. So there are 3 basic topics when it comes to calibration of HAWC data. One is instrumental polarization, second is opacity correction, and third is flux calibration. But to be honest, the opacity correction and flux calibration are identical to what forecast instrument does. So we have same calibration procedure for most of our imaging instruments, and since forecast was the first one, that's where we developed all these techniques. The techniques are not, I don't want to say it's something novel. It's a standard calibration procedure for any of the mid and far infrared data, so it should be straightforward. The only difference for HAWC is, since HAWC is a polarimeter, we need to be careful about the polarimetric observations and careful about instrumental polarization for to take account of instrumental polarization. And if you need more details about how the opacity correction and flux calibration are done, you can look at the 2 references listed below, the paper by Herter et al., the forecast data handbook. I should also mention that the forecast data reduction pipeline is now available for public. So if there are people in the audience who likes nitty-gritties of coding and want to see how the calibration is coded, you can look at the pipeline, and this will be identical to what we have in the HAWC. HAWC pipeline is not yet released, but we are in the process of finalizing the last step so that it will be released to the public soon. But I don't have a date yet when that would happen. All right, so let's start with Stokes parameters. So as I mentioned, we have 2 arrays. We talk about R array and T array, and when we combine it in various format, and this the angle here refers to half wave plate. So the way it functions is, you first choose a filter to observe your source in, and then if it's a just a flux observation, if it's a total intensity observation, then you just measure your R values and T values, whatever you get, and you generate your flux, which you can refer to as Stokes I. But if you are doing polarimetric observation, then you have a half wave plate which you rotate through different angles, and the angles are listed as a subscript here as 0, 45, 22, and 67. Again, these are the standard angles you use, and you can get your Qs and Us. Those are Stokes Q and Stokes U. And here I also list how to get your uncertainties in IQ and U. And since Q and U are correlated, you can have your correlated matrix here. So once again, if you need more details, look at the references listed here. So this is what level 2 data is. This is what we get in our pipeline as level 2 data. But now we have to go ahead and correct for it. In case of total intensity, you just get the first part of this equation. But if it's polarimetric, then you get the entire matrix, including IQUs and their associated uncertainties. So what's this instrumental polarization? So when you're observing an astronomical source and you measure a polarization of an object, you need to make absolutely sure that your polarization is from the source itself and not caused by telescope and instrument. The telescope and instrument almost every telescope and instrument will have some intrinsic polarization. They are usually small, but can be significant. And we need to make sure that we exclude these instrumental polarization from your astronomical sources. There are plenty of various methods which you can use to do that, but the two that we usually look at is the first is we look at the standard source observation. So we have standards that are observed in every series and in every flight, or try to be almost every flight. We take those standard and try to estimate what is the instrumental polarization, because we know that the standard should not be polarized. The other way to do is to take the telescope and scan along the elevation direction. So go from top to bottom or bottom to top and use that signal, that the background signal, as a model for your, and model it and get the instrumental polarization. So that's what I'll be describing next. So you can think of planets, moon, and minor planets as having very low polarization, or none at all. So when you observe these sources using HAWC and measure the polarization in the central few pixels, that polarization is basically coming from the instrument itself and not the source, not the planets or the moon. In case of HAWC, we use Uranus, Neptune, and some asteroids to look at this polarization. So what we do is we go ahead and do a polarimetric observations of the standards that we are observing, and the final product which we get, which is IQs and Us, we do basically a photometry of that signal, and we need to make sure that we are including the main beam as well as the first area ring, so the entire source is integrated, and you measure your IQs and U to get your instrumental polarization Q primes and U primes. Once again, these are standard polarimetric technique. There's nothing new here. So we have done this for plenty of measurements of our standards, and we find that typically Qs and Us are in the order of about 0.5% with a 0.3% standard deviation. This is a good observation if your source happens to be a point source too, just like our standards. Then you know where the source is. You can compare your instrumental polarization and say, okay, this is fine. But if you are looking at extended object on the entire array, then this doesn't work very well because the instrumental polarization varies where you are measuring it on the array. So this is good for standard for point sources, but this is not a good method to use for extended sources. So to measure extended sources instrumental polarization, what we do is we use what we call pole dips. These are basically, as I mentioned, move the telescope along the elevation angle, and when you're moving, you continuously rotate the half-wave plate angle. So the half-wave plate angle goes through four standard angles, and you collect the data continuously. Now, the signal that you measure on your detector is a combination of multiple things. Uh, it, uh, Two of those signals, which appear with a period of 90 and 180, has nothing to do with the air mass where you're seeing, but it's basically the telescope that is the the instrumental polarization that you're observing. There is one component which has to do with the with the air mass, and the last one is the temperature of the detectors itself. So we model all of these things, and then from the model we fit the data and get our q primes and u primes. Again, if you want to look at the detailed model, how this is modeled, if you want to understand more details of it, I urge you to go and read these two papers, Harper et al. Or Gordon et al. Both of them have very good description about how this is done. Uh, uh, so again, I urge you to look at those. In this case, when we have, again, we have measured this for lot of different series, lot of different flights, and depending on which epoch and series you measure, we measure the Qs and Us between 1.2% and 1.8%. So you can see that this can be quite big in some cases, but yeah, if you take into account your instrumental polarization, then you can correct it in your astrophysical sources, which is again a standard procedure where I'm giving the equation. The Q that you're seeing here, the unprimed Q, is the observation that you have. Q prime is the instrumental polarization. So you use that to correct and get your astrophysical signal, which is capital Q prime and U prime. So that's as far as IPs are concerned. Then we take the data we have and we correct for opacity correction. What is this opacity correction? It's basically, since we are observing your sources in different atmospheric condition, whether it be at different altitude where the plane is or different elevation angles, we need to correct for those for the atmospheric constraints. So to do that, first we compute what the atmosphere itself looks like, what it absorbs, and we do that using an ATRAN model provided by Steve Lord, which for attendees who were here yesterday, Dario talked quite a bit about it, and he had given some references, and I've listed down here some references too. So please take a look at that. What we have done is we have made a grid of ATRAN model at various altitudes of the plane, elevations of your source, and the precipitable water vapor along the line of sight. Once we have that, we can calculate the variations in the instrumental response at this various altitude and zenith angles. So once you get your data, we look at what altitude and zenith angle your data was observed, and we take a ratio of what the instrumental response was at that altitude compared to some reference, which in our case, we take as 41,000 feet altitude and 40 degrees zenith angles. Once you get that ratio, that's basically the ratio where you need to correct your data from. So we apply that ratio directly to IQ and U and propagate in its error, and that's how we figure out, that's how we correct for opacity. Last but not the least is the flux calibration, which is the most important part of any astronomical observation. And as I mentioned before, when I was talking about instrumental polarization, we use Uranus, Neptune, and some of the asteroids to measure that. We model Uranus and Neptune using Mueller's model, and for asteroid, we use a standard thermal model that was developed by Bill Waka, who is a staff scientist at SOFIA. And we get the distances of this model when it is observed from JPL horizons, so that we can scale the models to the appropriate distances. And once we have that, we multiply these models with the instrumental response curves for each of the passbands, integrate over it to get a photometry point. And that's your truth. That's the truth. And we have the measurement. So when you take a ratio of that, you get your reference calibration factor. Again, we do the reference calibration factor at a given altitude and zenith angle, same as before, uh, uh, before we did for opacity correction. Once you get your reference calibration factor, you just divide your IQs and Us with the factor to get your true calibration of your source. And the same thing, you propagate it through all your uncertainties. So now that you have your data, this all is done. how do you check for these calibrations to know when this was done or what was done? So to do that, you have to look at your level 3 or level 4 data, and you have to look at the FITS header. Level 3 and level 4 data come to you as FITS. So you can use any FITS header. You can use DS9 or FITS viewer or FITS header like the one Dario showed yesterday. And the first thing to look for is date. You query for date, and you'll see that the observed date was on, in this case, it's on December 7th, 2021. Once you have that, you can look for your keyword, fits keyword, call it config vals, which will tell you where the when the different series were run for HOP. So for example, in 2018, in August, in 17th to 11th, we had OC6K. That was an OC6K series, then so on and so forth. If you look at your observations, let's assume this is yours. So it is 2021 1207, which falls between this last line here, between 2027, December 7th and December 9th, which is an OC9H series. So you'll note this date to understand that that is the series that you're run. And the reason you need to know this is your source is calibrated using the standard observed in that series. So if you need to go back to look at the standard, you need to know what dates your source were, or what date those standards were observed. And since we are observing the same standard through all the series, this becomes important. The last thing to look for is you can query for cal factors, and you'll see fits headers like this. This is the calibration factor that was applied to your data. That's the uncertainty here. So when you finish your analysis and you say, let's do some photometry on your HAWC data or something, you need to make sure that you include this uncertainties in calibration factors with your analysis. It also gives you the reference values where these calibrations were done, the color correction, so on and so forth. It also gives you which file the data was removed from. So when the pipeline will be available for people, this file will be included with the pipeline, so you can go and look at what the values were in those pipeline. So once you have that, and if everything looks good with your data, you're great. But if you have any questions about calibration, or if you want to look at, oh, what sources were used in my calibration, you can go to URSA database. You can query, for example, here I've done an all sky query with the dates that I found above, which was OC9H series, and I'm looking at all the all the data from HAWC instrument. When you query this, something like this pops up, and if you look at your AOR tab, then scroll, then underneath you will see a lot of our sources like Neptune, Uranus, so on and so forth, which are our standards. So those are our standard observations. So you know what the AOR numbers are, so you can either download them, take a look at them, or see if they have any uh, if there are any issues. One thing I would like to note is that these are the AOR numbers, and all the AORs that start with number 90, that is cycle 90, those are all calibrations. So regardless whether it is HAWC, forecast, or any other instrument on SOFIA, when it starts with 90, that tells you that it's a standard observation. So that's another way if you want to detect them or filter your data here, you can do that. Then you can go and look at the HAWC panel. And in the HAWC panel, there are individual measurements. And when you highlight, it will give you on the right-hand side, it will give you all these information, which will tell you on which flight it was observed, what mode it was observed in, what filters you were observed in, so on and so forth. That's one way of looking at what standards were used for your observation. But one thing that I say is that there's always, when we get our data, the Sophia team spends a lot of time making sure the quality of the data is the best we can provide. And if there are any issues, whether they be calibration issues or any other observing issues, we note that and have a note in the data itself, in the FITS header, and that comes out as a quality assessment tag here. So if you are in URSA and you see this and you click on the quality assessment tag, it will uh, pop up a window where you can see what issues are. So that leads me to the known issues document. I have only a few slides left now, so I'll go through that. So once you know once you know what your issues are, you can look at the known issues document, which is a live document that is kept on SOFIA's website. And here you can see that we have listed various series, various flights, and the issues with those flights. When you click on the issues, you go to the details page, and that's where you can read what those issues were or what those artifacts were. So some of the artifacts that is listed on this known issues documents are as follows. So one is this, what we call dark artifact. This happens mostly with when you do a on-the-fly scans. If your scans do not contain true background, then when you observe an extended source, you get this dark lines around your extended source, which are basically artifacts because the background is not estimated properly. So one way to avoid this is to make sure that when you're designing your experiment and when you're designing your observations with SOFIA, make sure to include a true, I make true in quotes, true background so that these artifacts don't show up. And this is a common occurrence because, as you know, in mid-infrared, we have a lot of extended sources. So sometimes to get true background is hard, but rule of thumb is to at least get to a background flux level, which is about order of 10 less than your peak source. The other artifact you see is in imaging mode, and this is basically where the telescope did not scan very well. There were some issues with the telescope. Again, in this case, it's a rare occurrence. This doesn't happen often, but this is a point source, so I don't really care about what happens here. But if you had an extended source, then it makes life harder. So you'll have to either ignore this part or just use the good part of the data. The last one that I want to talk about is what chop not. Since we chop the telescopes, if your source is bright, then it creates these chop smear. This is not something that can be removed. Again, this is a very rare artifact. Happens only when your source is extremely bright. And you may also see something what we term as band A ghost. This happens in band A of HAWC. This is basically from an internal reflection. And once again, these are hard stuff to get rid of. So if you do have these kind of artifacts in your data, then you need to be careful when you do your analysis, and you need to address these issues when you are publishing it in your paper. I'm already on my time, sorry about that. And I'll take questions on Slack if you have any.